example 6.14, but we're first going to be looking over 6.5.9, which is the application of small signal equivalent circuits. So these are some steps that we can go to solve problems like this. The availability of the small signal BJT circuit models makes the analysis of transistor amplifier circuits a systematic process. The process consists of the following 5 steps. So first, we're going to eliminate the signal source and determine the DC operating point of the BJT, and in particular the DC collector current IC. So we have to also note that DC voltages we replace them with shorts, and DC currents we replace with opens. We're not going to have any in here, but that is just important to note when we eliminate the signal source. We're then going to calculate the values of these small signal model parameters. So GM is equal to our IC over VT. We have our R pi, and these are in the notes linked below the like button, but I've also included them here. We're going to ignore the T model and also find our R naught if needed. We are going to eliminate the DC sources by replacing each DC voltage source with a short circuit, and each DC current source with an open circuit. Talked about this right here. So this is the same as like step 3. We're going to replace the BJT with one of these small signal equivalent circuit models that can also be found in the notes linked below the like button. Although any of the models can be used, one might be more convenient than the others for our particular circuit for the values that were given. We're going to analyze the resulting circuit to determine the required quantities. So like voltage gain, input resistance, this process is going to be illustrated for us in the examples. So the first one is what we have here. Now this example is not great because of the forcing of our IB, making IC depend too much on it, and we don't want that. So our beta is, if it changes, our IB is going to change drastically, and that is just going to be something that we don't want to do because we want to be more independent of our beta. So if we look at the circuit we're given, it's going to be something that's on this right here, which is going to be an NPN in the forward active region. So we know we have our C, which is the collector up top, and we have our E, which is our emitter down below here. So we're going to follow the 5-step process outlined above. The first step in the analysis consists of determining the quintessential operating point. For this purpose, we assume that our VI is equal to 0, and thus obtain the DC circuit shown in the figure. The base current is going to be the following. So our IB, and we'll come back to this in a second. The reason why we're setting our VI to 0 is because we are just, like we said earlier, DC voltages are the DC voltages are replaced with shorts. So we are not going to have anything here, and we're going to short this out, and so our VBB is just going to go straight into here. Now, with that noted, we are going to continue looking at our IB. So our IB is going to be the current that flows over here. Well, IB, if we use Ohm's law, is going to be the voltage of the source, which is our VBB, minus the voltage of our base emitter, which would be like right here for this. And that's going to be at 0.7. VBE is always at 0.7, and that's in the notes. We've also covered this previously. That's what we're going to be using. And so we have this over our RBB, which is the resistor in between them, kind of like a voltage divider is what we have here. And then we set it equal to 0.023 milliamps. Now I said voltage divider, but we are not using a voltage divider. We're using Ohm's law. So the DC collector current is going to be the following, and the DC voltage at the collector is going to be the following. I'm skipping the DC collector current because that is just plugging it into the equations that we have here. That's on page 103 of the notes. Now, important to note, for when we're dealing with our VT, which we're going to come in a second, I just wanted to make mention of it now. This VT is always going to be 25 milliamps. Sometimes the author writes it as 26 milliamps, or millivolts, and that's okay too. But looking at the DC voltage at our collector, we have our VC is equal to VCC minus our IC times RC. And this is basically just getting the voltage of our current, right? So what we have here is we know that we need some VC right here, right? And we know we have some IC flowing through it that we haven't found yet. Well, if we want to find our VC right here, it's just going to be equal to, like how we said it, VC is equal to the source current, so VCC, we can write this as source, minus the current that's lost over here, so lost, or the voltage that's lost, voltage lost. So we have our VCC minus our VC, and that is going to be the base VC that we're looking for. That's going to be a 10 volt for the start. We have our resistance, which is 3 kilo ohms. And then we have our IC, which I guess was not given to us, but we found it right here. We're going to be using our IB, and that is from the notes again over here. And with our IB, we're able to find our IC. So IC was found right here is 2.3 milliamps with the equation, and that's going to give us 3.1 volts. Since our VB is at a 0.7, which is right here, it's much less than our VC. It follows the quintessential condition that the transistor is going to be operating in the active mode. So we're going from the emitter to the base to the collector. So that's the active mode. And the DC analysis is illustrated in figure B. Having determined the operating point, we can now proceed to determine the small signal parameters. So we have our RE, and our RE is just going to be the resistance over our emitter. And the resistance and the emitter is right here, so the resistance over this area is just going to be the voltage T, so that's going to be the 25 millivolts. Over the current flowing through it, our IE, and we can find our IE from the equations. It's going to be 10.8. Same thing with our GM and our R pi. We'd find it from these equations around page 104. So we keep going down. We have another note about the DC voltage and currents as shorts and opens. And then we're going to rewrite our circuit. So replacing our VBB and VCC with short circuit results in the circuit that we have here. So again, our VBB and our VCC are going to be short circuits. To carry out the small signal analysis, it is equal conveniently to employ either of the two hybrid pies, equivalent circuit models of our figure, to replace the transistor in our circuit, using the results in the amplifier equivalent circuit given in figure 6.42d. The analysis of the equivalent circuit in our figure proceeds as follows. So we have our VBE equal to, and then we have the equation right here. So the reason why we're going to get this is because if we rewrite this like how we have here, and this can be found in the notes like how we would rewrite it. If we do this, we only look at this part, this is going to be like a Thevenin equivalent. So we have to find this, right? The Thevenin equivalent, well, we would use, it looks like, the voltage divider, right? If we use a small resistor value, we would not lose so much signal. Note how small our signal is right here. If we use bigger resistors, we would not have such a small value. We wouldn't lose so much signal here. So our VBE, which is the voltage right here, is going to be equal to our source, which is our VI, times the resistor that this is happening over, our R pi, over the two resistors. So the output voltage V out is just given by the following equation right here, and then we just plug things in, and the voltage gain is just voltage output over voltage input. That's always how it's going to be unless it's otherwise specified, which is negative 3.04. And that's going to be it for this problem, how we find the specific parts, and how we would demonstrate the application of the small signal equivalent circuits.